Fred is what you would really call a capital person. He did his undergraduate work at the University of Ottawa. He did his graduate work at the University of Ottawa. He did a postdoctoral fellowship at NRC in Ottawa, and then he joined permanent staff at NRC in Ottawa. Okay. He's a member of the Ultrafast quantum photonics group, something like that.
Exactly.
And which is a very, I visited them a while back. It's a very interesting group of people and team and projects they're working on. And he's going to tell us today a little bit about programmable ultrafast photonic quantum circuits. So please join me in welcoming.
Thank you. First of all, thank you very much for the invitation. I had a very nice discussion yesterday and this morning. Saw a great lab, so it's very a pleasure to be here. And so yeah, so the title of my talk is why Ottawa is a great city and there's no reason to leave. And so maybe the best reason to be there. So okay, I'm part of the Ultrafast Quantum Photonics group, which is a research group at the National Research Council. This is our building in Ottawa. And so our group is made of 5 staff scientists and about a dozen of postdocs and students. And for keen eyes, you might recognize this person here, Milica Banish, that was actually that did her PhD here. She's not an experimentalist. So really, this is the Ultrafast Quantum Photonics and theory group. So, so there's some theory people. Which is to say, we work very closely with the theory group at the NRC. So there's this very tight collaboration with them has been very useful. And our labs is we have many lasers and detectors and yes.
Is your lab housed in that whole building?
Yes, yeah. We're in this building.
How do people experiment conditions?
We're in the basement. That's always the answer. Yes. No, it's yeah. It's a very nice building. So this is a picture of inside the building. So we have lunch in the library. It's very nice, but it definitely takes a lot of maintenance. And yeah, but the lab conditions are pretty good. We're putting quite a bit of time and energy in making sure everything runs smoothly. But yeah, and so maybe just to give you a bit more context. So the NRC has a long history in ultrafast optics. So starting from Hertzberg and there's Paul Corkum, if people are aware, he's pretty big in atto science. And basically the lab we're in right now used to be an ultrafast optics lab, but about 15, 20 years ago, it took a turn to do more stuff towards quantum technologies. So the group has been growing quite a bit every year, and we're doing more and more quantum technology things using ultrafast optics. So a lot of the expertise and the knowledge in the group and in the building is how to run big ultrafast lasers and then how to do experiments with them. Okay. So probably don't have to spend too much time on this slide, but usually you have to explain to people, like if you want to do quantum technology, there are different systems. And the one we're interested in is photons. We can actually do experiments only with light. And I would say most photonic quantum technologies application, you can actually think of something like this, where you have some Gaussian transformation, which kind of looks like a chip, actually. What this is well, there's a passive part where you should be able to make arbitrary unitary transformations. So those are phase shifters, beam splitters. There's also an active part in this Gaussian circuit, which is squeezing, so single mode squeezing or two mode squeezing. You have your input states, which very often is just vacuum, especially when you're using parametric amplifiers in your Gaussian circuit. But it can also be single photon source, some like quantum dot or other types of sources. And then the output at some point you probably want to detect. So there are different types of detectors, homodyne, p-90, so photon number resolving detection. So this can be done with transition edge sensors or conducting nanowire detectors. And really, this is how we look at most of our experiments. And so, for example, if you take quantum sources, if you want to have a very bright squeeze source, what this is you start with vacuum. You want to make sure you have a Gaussian circuit that makes you a nice, pure squeeze state. Then you want to be able to measure it. Quantum memory is essentially making a transformation that keeps the input photon statistics and take it to the output with some delay that is controllable. Quantum communications just want nothing, just want to be able to send something and have the same thing coming out. That's usually not the case. Quantum sensing is where you have a parameter you want to sense, and you encode this into some sort of transformation. And then hopefully, if you know the input and the output from those measurements, you can figure out what this unknown parameter is with high sensitivity. Networking, maybe your outputs are at different locations, and quantum processing or quantum computing, this is maybe the obvious one where this actually looks like what some of the people building or trying to make quantum computers look like. This looks like. Okay. So I'm in the Ultrafast Quantum Photonics group. So we're basically trying to look at how we can build something that's general, where we should be able to touch all of these applications, but with ultrafast light. And the name of our approach, if you look at the first letter, makes poutine or poutine. And what I'll do, I'm not going to read it, but I'm going to go sort of word by word in the acronym and just walk you through how we approach these things. Okay. So the first thing is temporal. And very often when people say, okay, light is great for many things, what they'll point to is the bandwidth. It's very fast. It's going speed of light. It's very fast, high bandwidth, which means you can repeat things many, many times. Another way to look at it is you can have short pulses, so you can really compress a lot of the information. So high bandwidth really translates to time. So if you want to take advantage of light, very often makes sense to look at the time domain. So your input modes that I had in my Gaussian circuit, they can be any degrees of freedom of light. So if you have waveguides, these would be sort of position bins. But working with temporal bins actually have some advantages. And here I'm showing two different polarization per bin. So this is the first thing. We really like to use temporal encoding for the kind of applications we have in mind. So the second thing is interferometry. So as soon as you have some quantum application in mind, you will have to interfere different modes. So this is sort of the simplest version of the beam splitter is the first thing you want to do. It's relatively straightforward how you do this here. You just mix two position bins on a beam splitter and then look at the output. You have interference. In this case, not so obvious how you do this in time. So let's just go through a quick example. So time bin qubits. So time bin qubits, you have computational basis where you'd say, all right, my state 0 would be at a certain time. So early time bin and my state 1 would be at another time bin. This is fine. You can measure this with detectors, and whenever you get a click relative to some reference signal, that tells you your information. But you also need to be able to work in a superposition basis where now your photon is always in the superposition of two temporal bins, but the information is in the relative phase. So either you're oscillating in phase or out of phase. And then the question is, how do you actually measure this? So for position bins, it would be an interferometer. But here, what you have is these things called time-delayed interferometers. So the way it works is you have your two time bins, you split them, you shift one by exactly the amount that they're separated, and then you re-interfere them. And the important part is you actually need to have this time delay to match the timing difference between your two time bins. So for a nanosecond, this would be something like 30 centimeters. You have this time delay interferometer, then you look at the output port, and in this middle bin here, depending on whether it comes out in here or there, that tells you whether it was in phase or out of phase. Unfortunately, these two non-interfering bins doesn't really give you information about the superposition basis, but it does tell you information about the computational basis. So if you think of, I don't know, quantum communication, people wanting to send qubits in time bins, this is actually how they do it. So they'll send two time bins in a fiber, and then at the output of the fiber, you have something like this, and then you can just measure. Okay. Yes.
First one is computational. I think of, I'm a theorist, so I think of zeros and ones.
Yeah, exactly.
The superposition is also 0 and 1, it's still different from the first one. So is it like multiple qubits per se?
No. So it's still one qubit, but it's in the superposition basis. So if this is 0 and 1, the superposition basis would be 0 plus 1 and 0 minus 1. So 0 would be this bin. So 0 plus 1. So plus means that they're in phase. So you have a superposition of the two time bins, but they're in phase. And in this case, it's just 0 minus 1. So they're out of phase. So then when you interfere them, you actually get destructive interference at one of the output ports.
Why do you want to interpret?
Yeah. is the most basic thing. Like if you're saying that, okay, this is going to be a nice family of modes to encode information and to measure, you at least need to be able to interfere. This is kind of like the first thing you want to be able to do. But we're gonna build up to more stuff. But like so if you want to do quantum key distribution, this is like a very nice degree of freedom through a fiber instead of polarization. Okay. The next one is ultrafast. Okay, so I basically said they're separated by a nanosecond. I didn't say why you pick a nanosecond, but what people like why this has been the time bin separation of choice for many years is single photon detectors like APDs, they have timing resolution or timing jitter on the order of a nanosecond. So you can just basically directly measure time bins on the computational basis with these single photon detectors, but then your time delayed interferometers are big. It's like 1 nanosecond is 30 centimeters. The other thing you can do is to say, well, if I have a pulsed laser with some repetition rate, so if you have an 80 megahertz oscillator, you're going to get pulses every 12.5 nanosecond. You can say those are my time bins, which is fine, because so your detectors will definitely be able to resolve 12.5 nanosecond. But the issue now is what this corresponds in terms of delta T now is several meters. And now you need something that's, you could try to build a free space delay line that's 4 or 5 meters long. But what people have been using is fiber loops, which is fine. But now you have to basically treat this as big interferometer. So what people usually have to do is they have to send another laser at a different wavelength, and then you try to lock the phase. So this is doable. The nice thing is you can have now phase modulators that can address the phase for each time bin. And so we're in Toronto, so Xanadu actually, if you're familiar with the Borealis, it actually looks something like that. Okay, so nanosecond, but we now have detectors are a little faster. So still going with the timing resolution of your detectors. If you have superconducting nanowire detectors, now most of them can get resolution on the order of 100 picosecond. So now that means that you can maybe go to the integrated regime, so you can have integrated the ley lines, so more compact, less phase drifts, you don't have to stabilize them. So this is getting nicer. But we're in the ultrafast regime, so our pulses are 100 femtosecond or a picosecond. So why not go all the way to picosecond time bins now?
So I thought like these ultra fast pulses, their pulse duration is 100 picoseconds. So like it's also the repetition rate.
No, so when people talk about ultra fast lasers and ultra short pulses, usually they mean on the order of like 100 femtoseconds or picosecond. So the in like in duration.
Going to two distinct.
Yep.
Okay, so like when you're drawing all these pulses, that's not.
So this is the separation.
Like separation by doing what by doing this interference trade, like by doing interference.
Yeah. Sorry, yeah. So here would be basically the repetition rate of your laser, but here you'd have to make the train of pulses probably with something like this.
This right?
Yeah.
Because all of that pulse laser will automatically train, but that's not a train you want.
Exactly. But I mean, like there are gigahertz repetition rate lasers, so then you would have nanosecond. But yeah, most of the time it's 80 megahertz and lower. But yeah, so definitely in this regime, this is not the output of your laser. You have to make yourself this train of pulses separated by a few picoseconds. And now the very nice thing is when you're down to a few picoseconds, the kind of delays that you need is not 30 centimeters now. It's going to be sub-millimeter. And actually, if you look at a birefringent crystal that's only a few millimeters thick, the group delay you get between two polarization is enough. Like this is actually what you need. So now this big thing, or like this big thing, you just put a birefringent crystal. The way you tune the reflection of what you would have in a beam splitter, you just rotate your birefringent crystal, and the relative phase you tilt it. And this is basically stable forever because things stay, they don't rotate for no reason. And then if you want to have twice, like another time delay interferometer, you just use another crystal that's twice the length. But now the issue is we don't really have detectors that can detect single photons with picosecond resolution. We have detectors that in our lab that have timing jitters on the order of like maybe 20 picoseconds. So we're actually trying to see whether we can have thick enough crystals so that we can still directly measure the computational basis with our detectors.
I'm confused.
Yeah.
These hybrid crystals, we know they can add phase shifts,
Yeah.
but I think what you want to do here is use group them.
Yeah.
So I don't immediately see that connection.
No, so they also produce a group delay. So if you have a crystal that's birefringent enough, so here we usually use alpha VBO or calcite. They will actually give you 10 millimeters of alpha VBO will give you 5 picosecond of group delay plus a phase shift. But the phase shift you can compensate by tilting them a little bit. Yeah.
That still makes the device giant. Like 5 millimeters is not microscopic.
No. So yeah, this is all free space bulk. Yep. Yeah. But in terms of, I mean, like this is, yeah, this is integrated. But if you're in the lab and you want to do experiments with your lasers, like you don't have to couple to a chip. You just put your alpha BBO, it's AR coded, you can tilt things, and you can start to, depending on your application, you can start to make things that are interesting. Yeah. Okay. So the question is, how do you actually measure different time bins that are like picosecond with, like, if you don't have detectors that can resolve these things? Okay, but before I get there, maybe I can mention a few other reasons why we're interested in ultrafast. And one of the things with ultrafast lasers and ultra short pulses, you're actually compressing all the energy in a short pulse. You have high peak intensity. So that gives you access to nonlinearities. So if you have bright pulses, you can change, some properties of the material. And if you, so one of the things I was mentioning was parametric amplifiers or squeezers. If you have high peak intensity, you can squeeze things harder. So if you want to go in this regime, ultrafast lasers are probably the way to go. So this is one example of something we like. I think this was with 100 nanojoule of pulse energy, you can get squeezing where your mean photon number goes relatively high. Another nice thing is if you have a short pulse that's Fourier transform limited, this actually allows you to be in a like single mode regime. So for those who are familiar with these kind of plots, the joint spectral intensity, so you can have round JSIs, which means you have high spectral purity, so low Schmidt number, if these words mean anything to you. And also for keen eyes, we don't have sync lobes, which you usually have with crystals. This is because we actually work with these aperiodically pulled crystals, so we can actually turn on and off the phase matching in a Gaussian way. So that way we can get rid of the. And the trick is you just match the pump bandwidth to the phase matching bandwidth of your crystal. And then finally, this is a cool one. So I've been talking a little bit about photon number resolution, which you can get from transition edge sensors, but they're big, they're expensive, and you have to run them very cold. Another type of detector is superconducting nanowire detectors. Most people think of them as click detectors, but if you send single photons or pulses that are short enough, if you look at when they give you a click, this actually gives you some information about the photon number in the pulse. And so what's going on actually is if you have more photons, the signal you get out of your SNSPDs will rise faster. You're going to cross the voltage threshold faster. So just from that information, you can get some PNRD out of it. And this doesn't work if you have long pulses. So this only works when your pulses are quite a bit below the timing jitter. So in this case, if you have very fast SNSPDs and you're like on the order of picosecond or smaller, you can start to resolve more higher photon numbers. And this is nice because you can run these at a couple of kelvins, and yeah. So that only works with ultrafast pulses. Okay, but how do you actually measure them? So let's go to optical, which, okay, obviously this is photons, it's optics, but what I mean is really all optical. So if you think of different types of modulators, you have boosto-optic, thermo-optic, electro-optics. These would be like your Pockels cells, and they all have different speeds. And there's another type of modulator called all-optical modulators. And this is where light modulates light. And most of them, or the type of all-optical modulator we're interested in, This is based on a Chi3 or Kerr nonlinearity, where you have a bright pulse that induces a change in refractive index that's sensed by a less bright pulse. So this is cross-phase modulation, and these are the kind of phase shift you get. And what you want is you want a bright pump, but also a long interaction length and some nonlinearity. And one way to do this is in a fiber. So fiber will give you high intensity over a long distance. Okay, so imagine this. You have some quantum signal. So this can be single photon, squeeze light, whatever you want. Go through your fiber, and then it comes out. Nothing changed. Now, overlap with your single photon strong pump. And this is very bright. But it has to be at a different color so that later on you'll be able to filter it out. And now this, as it propagates through the single mode fiber, will induce a change in refractive index. This is an intensity-dependent refractive index change, so the N2I term. And this change in refractive index will be seen by the pulse. But since this is a short pulse, you're basically turning on and off this, this phase modulation on a very fast time scale. So it's basically on the order of the pulse duration here. And well, for those who are familiar with cross-phase modulation, you actually get a different phase depending whether you're aligned to the polarization or you're cross-polarized. So really what you're inducing here is a birefringence. So now you can think of the strength of your strong pump as the optical retardation of a wave plate that's very fast. And then the axis, the polarization is like the optical axis. So you can think of this as you put a wave plate and you remove it, but on a picosecond time scale. So yeah, so we can do polarization rotation. If you align it with your single photons, you just add a phase and so forth. Okay. Okay, so what can this be used for? So if you actually look in time, we can actually get this to be on the order of a picosecond. The first thing we wanted to test, okay, you have this very fast switch. If you cross-polarize your signal, then you only rotate for a picosecond. What can you do with this? And one of the things is when you think in terms of modes, of spectral mode, if you have something that looks like it's Fourier transform limited, you're near a single mode. So if you match that with a filter that is basically the bandwidth you had for a Fourier transform limited picosecond pulse, now you're filtering out with very high efficiency something that's close to an optical mode. Also, if you couple to single mode fiber. So one of the issue in quantum communication is if you do an experiment with a satellite, you have to do it at night because you have a lot of photons. So you can imagine you have your little quantum signal that's sitting on top of a bunch of noise, both temporally and spectrally. Now, if you go in, you turn on and off your all optical switch, so you filter out all the noise that comes before and after. So this is good, but you still have a lot of noise here. And spectrally, now you've just reduced a lot of the noise. If you then put a spectral filter, now what you see is you actually reduce the noise. So this allows you to actually look at single modes, both spectrally and temporally. So that was one of the first things we looked into. Now, the second thing is, well, this is only acting on 1 picosecond. So what if you bring another pulse at a different time bin that's separated by more than a picosecond? Now you're just addressing one time bin. So what you see is, well, now in our picture of a Gaussian circuit, now we have something like a phase shifter and a beam splitter that we can apply for different ultrafast time bins. And again, you can see there was some quantum communication motivation in the beginnings. You can actually use this to do a quantum communication with ultrafast time bins, and you can resolve your different time bins at the ultrafast time scale. Okay. And more recently now, so all of this, I should say, this has been done in the near infrared. So your pump is for the experimentalists in the room, your pump is at 800 nanometer. Your single photons here are at 700 nanometers. You want them to be far enough apart in terms of wavelength so that you can filter them out. Another thing is if you send a very bright pulse in a fiber, a lot of things go on. So you're going to have a lot of Chi3 processes that are going to be phase matched. You're going to get noise at some point that's going to reach the band, the spectral band of your single photon. So there's quite a bit of work that goes into how do you actually get enough nonlinearity to get a pi phase shift, but also you're not introducing noise photons. So you have things like Raman, you have things like so And there's also a whole thing about so they're going to have different group velocities. So they're going to walk through each other. So that's going to limit your interaction time. So you have to play with the wavelengths and everything. But basically, we had this switch that worked pretty well in the near infrared, but we wanted to bring this to telecom because we have these detectors that I've already mentioned. We can measure, we can do PNRD with them. So we want to have something where we could switch telecom photons. And so I mentioned 800 and 700. You often want your pump to be on the red side of your single photons, because you're going to get Raman noise. Raman noise is on the red side of your pump. So now with 1550, if you want your pump to be on the red side, you're in the anomalous dispersion regime. That's a little tricky because you're starting to make solitons and things like that. So instead, what we did, we brought our pump at 1 micron. So 1 micron is on the other side of the zero dispersion point. So now you can group velocity match them, but they're still far enough apart that you're not getting a lot of noise. So we have this 40-watt laser system where most of it pumps in OPA, so we can actually generate quite a bit of light at 775. This will pump our crystal that gives you single Schmidt mode source. So you can make heralded single photons or heralded photon number states or squeeze light. We can measure our herald with whatever detector we want, and then send our heralded state into one of these short single mode fibers, bring our 1 micron bright pump pulse, and then use this to do a polarization switch. And so if you increase the pulse energy of your pump pulse, you can reach 100% switching efficiency. This is the amount of noise, so you're on the order of 10 to the minus 5, so it's actually not so bad. So yeah, so we actually have a nice way now to measure single photon in the telecom at, with picosecond timing resolution. Okay, one more thing. So when you do these scans, and you look on a spectrometer, you see your single photons, the spectrum actually changes at some point. When they do a full walkthrough, it's not an issue. But if you don't do a full walkthrough, the spectrum changes. So we thought, okay, what's actually going on here? So think of, you have a single photon here. It's in a pulse, so this is the spectrum and frequency. And now if you add on top of that a slightly longer bright pump pulse, and you overlap it with a part where you have this linear gradient. So the intensity of your pump pulse is going up. And the intensity is proportional to the phase shift the single photon sees. So now you have a linear phase shift in time. And if you remember your Fourier shift theorem, a linear phase shift in one variable gives you a shift in the conjugate variable. So basically, it gives you a frequency shift. So we have a way to actually frequency shift our single photons. And if you change, and this shift is proportional to the slope of your linear phase shift in time. So if you change the intensity, you can tune the amount of frequency translation you have. And if you put it on the blue side, you get a blue shift. So we actually did this. So sorry, it's in terahertz, but I have another plot in nanometer. But we can basically shift our single photons by many times the Foley path max. Okay, so this is a Gaussian pulse. You also have a quadratic term here. So quadratic phase shift in one variable gives you like bandwidth expansion and bandwidth compression. So if you think of position and momentum, it's like a lens. So if you put a lens in position, if you look at the focus, you either get focusing or defocusing. So when we sit our short pulse here, you get bandwidth expansion, and you could basically take two pulses, and if you make a positive quadratic phase shift, you're going to get compression. And so we also measured that. And so now the wavelength. So you start at 1550. This is a plot of scanning the pump. So you're basically scanning your pump as you go through. So then you see everything. So you see some red shift, some bandwidth expansion, some blue shift, and then you come back. And so if you start with 1550 and you have maybe 20 nanometer bandwidth, you can actually shift not quite 100 nanometer off, but like maybe over 50. So you really get a large frequency shift. So this was a very nice result that we found. Maybe, I don't know if you can see, but there's this little line here. And we were wondering what was going on here. And actually, a Gaussian has linear and quadratic terms in the expansion. There's also a cubic term. And if you know what so the Fourier shift theorem, so for cubic terms, a cubic phase shift in time gives you airy patterns. So it's these kind of fringes that you have. So we can even make third order effect in frequency from this cubic phase term in time. Okay, so we with our platform we can start to, we can rotate polarization, can phase shift, we can change frequency. So now, I mean, this is all on a single or two modes. The question is, can you actually scale this to many modes? That's the network part. So imagine a network of beam splitters where you start with one beam splitter and put two beam splitters, all 50-50 beam splitters, and then the output here will interfere. And this is actually known as a quantum walk. So the question is, can we do this in time? So now your different modes are not positioned, but they're all in time. And we know that we can make beam splitters out of our birefringent crystal. And by rotating them, we're changing the reflection on our beam splitter. By tilting them like this, we can change the relative phase. So the question was, can we just buy as many of these birefringent crystals we can in a single order and just put them all in a straight line and then tune them to basically program some sort of quantum walk? And so we did this and it works. But the very surprising thing was the real question was, how stable would this whole thing be? Because you're essentially building, for experimentals in the room, you're building a 36 mode like multi-port interferometer. If you're trying, like even just a like 2-mode interferometer, it's kind of a pain. You have to stabilize everything. But essentially, since the phase and the coupling is set by the orientation, you can just mount them on some standard mounts and and it won't move. So basically, even after weeks, the phase of each of these elements just never change. Even to a point where we mounted them on these magnetic mounts where we could take them out and put them back in, and we're still in exactly the same phase. So you have this huge 36 multi-port interferometer, and you're like taking mirrors and phase shifters out and putting them back weeks later, and it's still exactly the same phase. So this is where we're like, okay, this intrinsic phase stability you get when you're building these temporal interferometers could be useful for some things. But when you rotate one of them, so let's say you're rotating this one, you're changing the reflectivity of all of them, the whole column. So you're not sensitive, like you're not selecting a certain mode. So it's not fully programmable in that sense, but you can program individual columns. So then to make it more programmable, we actually needed to go and add our all-optical switch to go and program different things. Okay, so if you want to make an arbitrary unitary transformation, you're going to need n times n minus 1 over 2 of these elements, which are beam splitters with a certain coupling parameter and a phase. And then this is called a Clemens mesh or rec mesh. So we want some version of this in time. So if you actually look at them, you can think of a 50-50 beam splitter and another 50-50 beam splitter. That's a Mach center. You just need to control the phase, the input and the output. So for us, the way this would look like, all of that is now just one element where you need to change the coupling for each of these, basically these time bins. So you can do this with polarization rotation. So you'd have your optical modulation that comes in. You change the coupling independently for every time bin. And then it's this part that's a little tricky because now you have to couple modes that are on different time bins. But it's not an issue because we can use one of our birefringent crystal, shift everything. And now basically we have, at first we had maybe this one, like we have to interfere with this one and this one. But what we do is we shift things. So now they interfere. And then you go with another round of these all optical switches. So in theory, we have this design where you could make any arbitrary unitary transformation with your ultrafast time bin modes. Okay, let's start with a very simple example. So you have two time bins. So your modes are, this is one time bin, T0, and then you have H and V. This is another time bin, T1, H and V. And then you just want to couple them. So the way it works is you bring one all optical switch, and then you change the polarization, and then you can measure each output. So if you start with no energy in your pulse, you just have the identity. As you crank up the energy, what you see is you have this sort of transformation that just swaps two of your modes. Then we did a similar thing, just measuring the stability over time. And this is essentially just measuring the stability of your pump laser. Just not bad. Okay, so something a little more complicated. So a Hadamard gate, where if you send a photon here, you end up with a superposition of all the other outputs. So I mean, so since you have the same coupling here, you don't need an all optical switch. You just need to rotate your alpha BBO or your birefringent crystal. Here you need a switch, and then you need another polarization rotation. So when we send here in the computational basis and just measure the output, what we see is we're on bias essentially. So we get 25% probability at each output. If instead we prepare a superposition of all of these modes, all in phase, and then 0, 0, 0, 0, 0, 0, pi, pi, 0, pi, 0, pi, and 0, pi, 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 0, and then just measure the output there, we actually see that we can interfere them and get basically the identity when you change your input states. And finally, we went for something a little more complicated. So this is 8 modes, and then we call these things permutation matrices, where you have some inputs and you just want to reshuffle them. And we're able to do so. You have your input, and then you can see they come out as some other output. And this is all in a single spatial mode. Everything is phase stable, just traveling through your experiment. So, okay. So I'm going back to this picture. So what we have now is we know how to deal with these input modes. We know how to detect them, although we're currently working on how you do homodynamics on them. But we know how to do PNRD. And we have the linear part. Now the question is, well, okay, this Gaussian transformation can also have active elements like squeezing. So we're actually going in this direction now to have these squeezing elements or interferometric elements in our circuit, but with ultrafast time bins. So I mentioned we have these squeeze sources. So the way they actually look like is you have a bright beam that you focus not too tightly in a crystal, and then what you get at the output is 2-mode squeeze vacuum. Okay, so you can think of this as this element now in your circuit. So the input is vacuum, vacuum, and then your output is a 2-mode squeeze vacuum. So one of the things we're doing right now is, okay, what if you want to stack 2 of them together? So now you just take another crystal, and this is maybe a bit of a technicality, but your output modes here, if you want them to line up into another crystal, you actually need to rotate your crystal. And if you do this, this pump laser pumps this crystal, and then this pulse pumps the second crystal. But the time bin separation here is a few picoseconds. So the way we make them is with our birefringent crystal. So we can fully change the relative intensity and the relative phase just passively. We just tilt things. So with what this means is we can do inline squeezing, where we have full control over R1 and phi1 and R2 and phi2, just the relative phase and the relative intensity of these two. And since our source are sort of mostly or close to single mode spatially, and they have these nice Gaussian modes, the output, they do overlap quite well with the input of the second crystal. So we have this inline squeezing, and this is result from only like 2 weeks ago. So we're very much still doing the experiment, but I just wanted to show some of the stuff we're currently working on. If you make your relative phase opposite here, you're basically making 2-mode squeeze vacuum. And you can actually undo your 2-mode squeeze vacuum to have some sort of glorified vacuum at the output if you're just measuring coincidences. So as you're scanning this, what we see is right now we're at 95, but we think that with playing with the alignment and the focusing of our pumps, we can get higher visibility. But now you can think of this as a nonlinear interferometric element in your network, in your Gaussian circuit. And you have full tunability on the strength and the phase. So not only can you have these like beam splitters and phase shifters, but now you also have these active elements that you can program all optically. So okay. And then you can think of, still with the 2 crystals, if the first crystal you pump it twice, you can have something like this, where you can independently change the squeezing in the phase. And then you can align your pulses. So now these 2 outputs becomes your input to this one. And this is another pump pulse. So you're all optically programming your circuit, and you also have access to this. And the output is actually like a large entangled Gaussian state. you don't really need beam splitters and phase shifters. And one of the things I'd like to do then is you can imagine doing PNRD on these different modes and then look at what's coming out here. And this is all going through these crystals that are AR coded. We have relatively high collection efficiencies. We're at like the high 60s right now. So we can maybe start to see some things by having everything is in single mode, single spatial mode, and you can program your circuit, then look at your output. So we're working on this right now in the lab. And then finally, that's sort of my last slide. There's a big G. So everything here is Gaussian, essentially squeezing and beam splitters and phase shifters. And I mean, in general, we'd like to make non-Gaussian states. And the way this often looks like is you're inducing non-Gaussianity from post-selecting with PNRDs. Or if you have something like a quantum dot source, you can get like deterministic single photons. So this is how you get your non-Gaussianity. One of the things we're interested in, maybe some people in this room are also interested in, is to see, can you actually start to get non-Gaussianity directly from your operations? And so like to give you an example, if you have something like pump depletion, when you're starting to pump your parametric amplifiers very hard, you start to see these non-Gaussian effects. But the question is whether it can be in a regime where you can actually measure this. And most likely, you want to have a lot of intensity to pump these things hard. So being in the ultrafast regime has this advantage that you're like naturally at the right in the right regime in terms of high peak intensity to do these experiments. So this is another direction that we're sort of going towards. And yeah, again, that's the group. So a lot of the work I've shown was actually done by Kate Fenwick. She's a postdoc in our group. Yeah, thank you.